Well, we can move on to Skully's talk next. I don't have a title for it. Sorry, Skully.
No worries. I think it's just N bodies. Okay. So at the end of September last year, after like kind of not being able to do much astronomy or anything during the pandemic, I started thinking about Newton's law of gravitation, and thinking about that basically he kind of used to describe the motions of the planets around the sun. And I was thinking about how kind of deceptively simple it is. So this is the equation. It's just F equals big G times 2 m's over r squared, where F is the pull of gravity, the actual force. So if you've got two bodies, it's the force that kind of attracts them to each other. Big G is just a fancy number that Newton made up to make everything magically work. The 2 m's are the masses off those two bodies, and then r is the distance between those masses. And so there's not a lot there. And I was like thinking about how kind of, yeah, that it should be something that I could actually put together and just make like a little simulation of multiple bodies, just applying this simple rule to move them around. This is actually not like a new thing. This is an n body simulation where you have n number of bodies and just let the simulation run. And you can see a kind of simulation of a galaxy here. Traditionally, these would be done offline, so like it just takes too much computing power to do, because you have to measure the force between every single one of these bodies, and so it gets complex really fast. But with the kind of improvement in computing speeds, some can actually be done real time. But if you want to get lots of bodies, what you really need is a GPU. The thing that I've made is running on the CPU, which is a lot, not as fast as a GPU at calculating things. But I just wanted to do this as a little kind of side project. But it very quickly I started getting excited about improvements that I could make, and then I realized I was losing a lot of time. This might be kind of ringing a bit of bells, because a month later we had a talk from Mike Peterson about basically simulating gravity. One thing to note though is that the simulation that I was kind of going for is literally just Newton's the formula that Newton came up with, but that's a big approximation based on his kind of observations of the solar system. But if you want to do a more accurate simulation, then you certainly won't go about it the way that I have, where I've used a game engine, and you also want to take into account other forces, because this is literally just gravity pulling it together. But as we learned from that talk, there's plenty of other things like the temperature of the bodies or gas, and like how the fluids move, and things like dark energy. And then we seem to be quite surprisingly simulation heavy, because the talk before that was also talking about modeling the birth of stars, where that similarly obviously had gravity was a big part of how they come about, but they also have to take into account things like ionization and magnetism. So there's a lot that you can put into a simulation, but obviously the more you add, the more complex it gets, the less likely it is that you can just make a fun little toy to play with. So like I mentioned, I decided I wanted to just use a game engine's physics engine. So a game engine is just a tool that you can use to make a video game. And you can there are quite a few popular ones, and the one that I use is called Unity. and it has a physics engine where you can basically take a body, attach physics to it, and then suddenly you can interact with it physically. And it does what's called rigid body physics. So you can have soft body physics, which is like squishy things, but that's quite complex to work out. And obviously, in a game, you want things to be real time. But what you can do is rigid body, where the shape of the body doesn't change, and it's a lot easier to calculate the physics off that. And they follow essentially Newton's 3 laws of motion. So if your physics body isn't moving, then it won't move, or if it's moving, then it'll keep moving in that direction unless something else acts on it. The second law, F equals ma. So you create a force is the mass times acceleration, or to turn it around, how much a body accelerates depends on the force that's been applied and how much mass it's got. And then for every action, there's an opposite and equal reaction. So if you push on a table, it will push you back. So just to kind of show, like, give an example of the physics happening in the game engine, you can see here that I've got 2 bodies, one that doesn't have any velocity, so it's not moving, and another that does have velocity, so it just keeps moving because there's no external forces acting on it. If I take 2 different bodies and attach, for example, like a rocket to them, if that rocket applies the same force to both of the masses, you can see that the one with less mass is accelerating quicker than the heavier, sluggish one. And then just to kind of show the kind of reaction, you can kind of have collisions very easily. I just literally attach rigid bodies to like the ground and the ball, and then turn on gravity, and then this ball will fall, and then it will hit the table, which will apply an equal force that will push it back up, and then it'll just keep going like that. This obviously doesn't model like losing energy to sound or heat or anything, so it's just going to keep bouncing happily along. And so I think, so now we have a physics engine, I can just take 2 bodies and just apply that Newton's force and just see what happens. It's not very exciting. So to make it a bit more exciting, because these are just starting with no velocity, so they just start accelerating towards each other, and then that's the end of that simulation. So if I instead apply velocity to one of them at like a perpendicular angle to them facing each other, then what you can end up with is this kind of orbit, which was quite cool to see. And you can also see that it looks like only one of them is orbiting and then the other one's stationary. But if we change our perspective to the other body, suddenly it looks like that body is stationary whilst the other one is orbiting, which is a kind of interesting artifact of change in your frame of reference. And then you can, so that's 2 bodies, and then I can increase it to 3 bodies. And anyone who's kind of familiar with the n-body problem probably can spot something that's going on here. So we've got these 3 bodies, and 2 of them are quite nicely rotating around, but they are very purposely placed with equal mass on exact opposite sides to each other, going the same velocity as each other, which means that they sort of cancel out, because the 3-body problem is that when you're calculating 2 bodies, they have very satisfying orbits, but as soon as you introduce a 3rd body, in almost all cases, that orbit just becomes chaotic. So I've got a video here of 3 bodies, what can kind of happen. And you can see that at the very start, it just goes crazy and one of the bodies gets launched out. I don't know what goes on there. But this is a video from a Twitter bot, where someone's got a robot that is just creating random initial conditions, and then just kind of lets the simulation run and kind of see what crazy orbits you can come out with. I'll put a link to where that Twitter is. Yeah, that's here. There's some other links that I put as well for, like, if you want to have a play around with something kind of similar. There's a few of these. There's also some videos of the more interesting n-body when you get to like the scale of a galaxy is always really fun to watch. There's also a video that someone talks about a really complicated orbit. So we're quite happy sat in our solar system with our kind of circular orbits, but after playing around with this toy, it becomes really interesting seeing how easy it is for the orbits to just go chaotic, and puts a little kind of worry in the back of my mind about if any of the bodies in our solar system decides to just sort of move a bit out of the way, and then suddenly everything collapses, which I'll show you in a sec. But that video, the complicated orbit, shows you, I think it's around the moon, or it might be one of the Lagrange points, but it just shows you the crazy shape that the orbit makes, and that's just where it kind of sits while all the different bodies in our solar system are tugging on it. And then at the bottom, I put a link to a video where someone's done essentially the same thing that I've done, but much cleaner, much nicer, and gives a really nice presentation of it. And that also does a really good job to show you the different frames of reference. So I'll now show you what the actual thing that I made. So you can just give it a number, however many particles you want to start with, and you can give it different kind of particle sizes, and it spawns it in like a circle of whatever radius you want. And they also have random velocities to just kind of start them off in a interesting room. Can everyone hear me okay, by the way? I've just seen that Jim kind of popped back in.
Yeah.
Cool.
Yeah,
Yes.
fine here.
Yeah, so if I just run this, you can see I've got a bunch of these bodies that have kind of spawned in a circle, and you can see they're all starting to pull themselves together. And you can see, yeah, they're starting to like form these little clumps. And so it's quite fun just watching these collapse into this big blob. But you can see that some of them don't quite make it in, and you actually end up with these orbits. That's probably going to make it in. But one of the problems that I came across is that if the size of the bodies was too small, then the physics engine started to do some kind of weird things where they start to get a bit aggressive and explode, which wasn't really what I was after. So you can see there that whereas the physics of the real world is time is continuous, for a video game, you need to do it in steps. So you kind of have your two bodies, and then you say in the next step, their velocity is making them move this much, and then the next step, this much, and then suddenly they're inside of each other. And so the physics engine needs to just gently kind of move them to the side. But when you have lots of tiny, lots of those tiny blobs, and they're all kind of clustered together, when you move one out of one circle, you move it into another, and basically it just gets very violent very quick. And so what I decided to do was make it so that you could sort of combine the bodies. So when two particles touch each other, then they'll actually combine into just one body. And so now what you'll see is that whenever one of these kind of touches it, then it will turn it will kind of combine into a bigger blob. And this made the simulation a bit neater, a bit nicer. You didn't have these kind of crazy volatile interactions. You just sort of had all the bodies just moving in a much nicer way. I also made it so you can see the trails. So that makes it a bit easier to see the actual orbits. You can kind of see some other laws of physics, of the Keplerian laws, Kepler's laws of motions, basically, where you can see it makes these ellipses, which is, as someone who knows about those, it's quite satisfying to see these forming. And what I was saying before about how volatile it is, you can see that these three bodies seem to be quite nicely in these orbits. But what's interesting is when they get close enough, because the distance between them is closer and is smaller, it means that the force that's applied is changes their orbit. Although that orbit didn't just change; they straight up collided with each other. But one of the things that came from this is just how mesmerizing it was to sort of just run this chaotic simulation and then just let it sort of work itself out, and then you just watch these kind of coming around, and it's quite fun to see. I've got those two the things that I showed you in the presentation, where, like say, looks like this outer body is rotating around this one, but if I change to this one, then it looks like this one's actually the one that's in the middle. But if I turn on the trails, then you get a bit better idea what's actually going on. They're both actually moving through space. And so it's quite interesting when you turn on the trails, how it sort of changes the perspective of what's going on. And also, I had my kind of stable three bodies, and those really are just rotating about that one point. Although if I look at one of the other ones, then that similarly looks like a kind of impossible orbit where those two are orbiting like in sync around that one. But when you turn on the trails, and that's when you feel like, actually, no, I'm going around this one in the middle. But if I take these same three bodies, so they're all the same mass, but instead of having them in line, I have them one of them at like 90 degrees, then you can see how like it suddenly stops being this kind of nice orbit, because they're starting to pull on each other in weird ways. I'll turn on the trails again, so you can just see that now they're all just going wherever they please. And because it's so chaotic, I was sort of curious as to whether or not I could actually have a normal solar system where chaos didn't ensue. Like, we've not only do we have like these bodies going around the sun, but we've also got moons going around the planets. Like, I was kind of curious whether or not I could make my own solar system. And so I had a shot at it, and then sure enough, I've got my sun here. So the sun's particularly large. And then I've got a planet going around the middle. And then I've got another planet a bit further out that has its own moon. And if I turn on the trails, you can see that they don't look like they are actually attached to each other. They look like they're sort of going, just sort of going in not very smooth lines. But if I instead focus on it and turn off the trails, then suddenly we get to a point where it just looks like this is just a normal, a bit basically what we were just looking at with the sun and the thing going around it, except that we're also going around that sun. And then similarly, we could have a larger body a bit further out. So because the distance is so important, if this body was kind of closer, then suddenly it starts interacting with all the other bodies, which is what's like I think quite important about our solar system. So one thing you'll notice is this isn't our solar system. I was wondering whether or not to do our solar system, but the sun has like 1 million times the mass of the Earth, which I just won't be able to represent accurately in a video game. And not only is the mass of the sun so massive, but the distances are such that if I kind of zoomed out enough for us to see him, it would just be a black screen. It wouldn't be very exciting to see. But just to kind of show how fragile it is, like these are quite nicely in their orbit. But if I was to, for example, make it just a wee bit smaller, then they still orbit. You might, if you're on this planet, you've got your kind of moon here, and you're quite happy with your moon. But then, to your surprise, it just suddenly decides to leave. It's gone. You don't have a moon anymore. So it's just quite interesting seeing how fragile it is. And I'm aware that there was like they think about things like the Great Bombardment, where Jupiter just kind of threw a bunch of rocks our way. And after kind of playing around with this N-body simulation, I can definitely see why. I know I've been talking a lot, but the last thing I was kind of say is, well, it was quite nice combining those bodies. One thing that was quite interesting about having them not combine is that when I combine the bodies, I basically make it so that the center of gravity is like in the center, whereas if I have a range of different sized bodies, then when they clump together, the actual sort of overall gravitational pull comes from like off center, and you get these different clumps of gravity, which is actually a better representation of the gravitable bodies. For example, like the moon, you can't really have a stable orbit around the moon. This is something that NASA found out during the kind of early like Apollo years, and prior to that was that they had sent satellites that they thought would be in stable orbits, and they after I think only a few days, they ended up crashing into the ground, and that's because they found out that's because the moon's like gravity like is not uniform at all, and so something like this body is a bit more kind of representative of it. And another thing that is quite nice about this is when not only can you see the spin of them quite well, but they also sometimes end up ripping parts off, and so you can get these sort of naturally occurring moons from the collisions, which is also a nice kind of aspect. But yeah, I'm sure I've taken up enough of your time, so I'll leave it there. And if anyone's got any questions, then I'll happily answer.
Yeah, that's great. Thanks.
Yeah, that's a bit disconcerting, though, Skully.
Yeah, a couple of comments I would make is that what you have with the clumping is very like what would happen when the solar system's forming, with planets being built up as stuff accumulates.
Yeah.
And I'd also say that I think there was famously proven by some famous mathematician whose name escapes me that the solar system is unstable, that inherently the orbits are not stable over a long period. I think that was, it wasn't Euler, was it? Somebody
I'm not sure, but yeah, it's an interesting thing, because I've kind of gone on a learning journey about orbits where like you start with Kepler's laws and you think, oh wow, it's actually really beautiful and really easy to kind of to work out what's going on. But then as you sort of dig more into it, you realize like, oh, actually no, like they can't.
You are but young yet, young man. Life is rarely in a straight line. We had many years ago, we had a speaker came to us whose subject was the N-body problem. You can predict what's going to happen with one body, with two bodies, but with three or more bodies, you cannot predict it. It has to be incremental. I think this is why you're getting on these models the ejection of an item from the original group, because he left us with a program which has just been written in, when I say basically, I mean, you could turn it into anything you wanted. It was for the BBC Micro. And I got a copy of this, and he had the X, Y, and Z, but the BBC didn't have a circle function, but the computer I had at the time, which I think was something like a 10 megabyte Amstrad at work, did have a circle function, quick basic. And I applied that to the size of the circle, the Z function, so it gave you the impression of depth from the screen, and it worked very well. But this was a feature that you could only run 10 or 20, or else you died of boredom because it moves so slowly. But on the other hand, if you had it moving too quickly, it tried to move through itself at the center. It's like the center of our galaxy. And you get these very close encounters. And of course, the mathematics becomes not representative of the real world at all. And I think this is why you get something happening that shouldn't be happening. You think, they just whip around one another unless they're within a solar radius sort of thing. But no, that's not what's happening. The mass are following it up.
That was actually one of the things that I was curious about when we had some of the talks from the other people who were simulating gravity, about asking how they deal with either collisions, or if they don't have collisions, then I was curious if they have exactly what you're talking about, where because the function is based on how close you are, if you get like ridiculously close, then the force suddenly kind of explodes because it's squared. So yeah,
but of course then you've got to calculate each point in turn. So does the next point calculate on their initial starting conditions, or on where the group has got to in its list of calculations before it starts again? It's a bit silly. You can only ever approximate it. And then
that's what I was saying about how it's not continuous. You need to do it in steps, and
then you've got to add
the smaller you make
relativistic
that steps, the more accurate it is. But it's always.
Then you have to start adding relativistic effects. Getting out to Uranus, Neptune, and Pluto is an amazing trick. I'm great admiration for the Voyager missions. Some computers on board that weren't much more than a ZX81, and they were reprogramming it as it was on its way, installing new systems. It was quite amazing.
Well, they're still reprogramming it now, which is a kind of interesting task. I wouldn't want that job.
Like you say, it's mesmerizing. You sit there watching it, says, is it going to, or isn't it? And then whoosh. And then all of a sudden it suddenly accelerates and whips off the screen. And it's gone. It's off to the next galaxy.
Some of them, it's quite interesting watching some get ejected, but it's also interesting watching some that are in a really elliptic orbit, and then something comes along and puts it in like almost a perfect circular orbit.
But that's how solar systems evolve, is that most of these interactions will end up throwing lots of garbage out into the interstellar space or into the sun, or in the case of the late heavy bombardment, into other planets.
Well, the elliptical orbits are always going to be unstable, aren't they? Because they will cross and cross and cross other orbits. As Skully was saying, eventually either it'll come to a disastrous end, or it'll achieve some sort of circular orbit that's co-orbital with the other members of the group.
Jessica's just showing me Lagrange, who I'm assuming is the person you were after, David.
That's the man, yes. That is,
Skully, can I comment on your simulation? I found it very interesting, particularly the one where you had bodies colliding with a central object and increasing in size. That, to me, was a black hole, wasn't it? Where the bodies are coming in and being whipped around and thrown out again, and if they hit the object, they obviously increase the size of the black hole.
It's a bit like that, although it doesn't become a singularity. So while the majority of that simulation was just run on that simple equation, when I did come to make them combine, I did also then need to program in conservation of momentum, because you could get kind of these two bodies hitting each other, and then what you would want is them to go off in the correct manner. So that's the only other sort of equation that I needed to also keep in mind. Otherwise, yeah, I was quite happy how just such a simple equation would result in this really kind of mesmerizing simulation.
Yes, is it an elastic collision like billiard balls, or is it two bits of soft plasticine?
Yeah, no, I don't.
All sorts of different things.
But you also had some that were chipping bits off the aggregate, hadn't you?
Yeah. So that's what I was saying about how, like, that's why I had a sort of check for whether or not to combine them, because sometimes I like seeing them combined, because then they sort of creates this nice clean looking like system. But then other times it's quite interesting watching the sort of colliding, and when I was watching them, it seems a bit more like how asteroids sort of come together. Like it seemed less like a system of planets, because they're made up of so much matter. It was almost nice just imagining them being these asteroids, and it's quite interesting watching them. If they get enough of a spin, then the sort of centrifugal force they start tearing themselves apart into these two separate shapes. And then as they get further away, then they obviously have less kind of gravitational pull, and so they can actually end up just sort of going their own separate ways. Or it's just it's almost like a really intensive on your laptop screensaver, just kind of watching these things go on.
It's a bit worryingly addictive, that though, because it is quite mesmerizing just watching to see where they go next. I mean, I'd be there for hours. I think I wouldn't start.
Yeah, I mean, I have been, which is really good during lockdown, when you're just like, well, should I watch what Trump's up to, or should I just watch some circles spinning about?
There's a quick question from Colin on YouTube chat saying, question of whether you've tried to model Trojan asteroid arrangements, or whether it might be something you want to actually try, where you have
it's definitely something I could try.
Yeah.
So at the moment, the way that I made that solar system was like through code. Like I say, I'm trying my best not to like make it into this huge project. I was like, I just want to create something with circles that just spin around. But as you get into it, you start wanting to do a bit more. Like what I would like to be able to do is sort of place the objects about and set the size and the velocity, and then let it go. And then it would be quite interesting to try and see if you could have some Trojan things that sit in like Lagrange points, because I believe it should be possible. But
serious danger of the what happens if and can't leave it alone questions.
But you will eventually come to the point, which I realized quite a while ago as I've got older. I used to think that if you could know the disposition of every particle in the universe, then you could tell the future. Until I realized, of course, intellectually, you have to have a computer to do this, which is probably the size of the universe. So do you include that computer in your universe? So then you have one of these fundamental philosophical problems. Yeah. And then I realized quantum uncertainty, and quantum entanglement. And I was really
now we're getting into deep.
It's all a bloody nonsense, and we've got Donald Trump coming up. Oh, not anymore. Well, he's not away yet. God.
Probably the scope of Skully's simulation to be able to model quantum effects at this stage. You're going to need a bigger computer.
And my final conclusion was that there's nothing in this universe you can't model with a ZX81 if you're prepared to wait. There comes very quickly the point at which you are quicker watching the real thing.
Yeah.
But on the numerical methods, there are quite a lot of systems that you can use, or methods you can use to actually cut down the calculations. If you really want to, you can find ways of optimizing grouping and I think a couple of our speakers that have talked about gravitational simulations have covered a couple of them. So,
at a distance, two galaxies have been treated as 2 points, but as they get closer,
Yeah,
you
exactly.
have to start breaking your galaxy up into how close the various components are.
Actually, that's another thing that I forgot to mention about when you don't combine in, is you get tidal forces, which is really quite cool. The points in that blob, the ones closer to it get more attracted than the ones kind of
There's
further
a
away.
gravitational
and when it's spinning,
gradient across the extended object.
So it's just interesting watching all these things that, you know, you see talked about, all these things that just come about from this really simple equation. So that's why I just thought it might make a nice thing just to talk through.
It's a thinking platform. It's gives you a jumping off point for thinking about things.
That's brilliant, Skully. Absolutely brilliant. Thank you ever so much. I really enjoyed that. That's terrific. Are there any more points and questions for Skully, or indeed any of the speakers that we've had? Is the chat thing okay, Dave? Yeah.
Yeah, there's just a couple of questions from Colin there.
Okay. What? I buckets of thanks to the presenters, because that really is great. Members' Night's always special, really, because I mean, I for one always leave feeling a bit motivated, because you pick up all these things that other people are doing, and it's just a lovely meeting. And even on Zoom, it still works okay. So that's just grand. That's just grand. But my thanks very much for the Zoomers who have given their time tonight. It was just excellent.